Hello and welcome to our presentation about the GPU shader compilation pipeline. I'm Mateusz, I'm developer technology engineer at AMD, and together with my colleague Nikolai, who's working in the shader compiler team, we're going to walk you through the whole shader compiler pipeline from high-level language source code down to ISA. We've split the talk into three separate parts. The first one is about the front end. Then we'll talk about static signal assignment, and eventually our journey will take us to the backend, where all of the dragons live and where the ISA gets generated. Before we get started, though, I have a small quiz for you. In this code here, you can see how many floating point multipliers do you see? I'll give you a few seconds to think about it. And yes, the answer is 4. There are 4 floating point multipliers in this code. And if you are as surprised as I am, then it's high time we take a look at how this actually happened. So what I didn't tell you so far is how I compiled this. And that's quite important, as we will see in a second. So this is HLSL source code I wrote, and then it goes through the following compilation pipeline. It starts with FXC, which is D3D11's shader compiler, which generates DirectX bytecode. Then the DirectX bytecode goes through the backend compiler, and that generates ISA. So we have to inspect every step along the way to understand where the floating point multipliers come in. This case it's fairly easy. If we just look at the generated DirectX bytecode, so the output from the FXC compiler, we can already see there's a DP4 instruction in there. DP4 stands for dot product 4, and that's where the floating point multipliers get generated in the backend because it sees DP4 instructions. Why FXC is generating this, we'll get to this later, but it's important to understand FXC has made this decision and the backend compiler is bound by it. Let's try with another shader compilation pipeline, in this case the Direct3D12 shader compilation pipeline. So we start with DXC now instead of FXC, which is the new shader compiler. It produces a different intermediate representation called Dixel, which is based on LVMIR. And that's the part of the code snippet here which relates to the vector addressing instruction we saw before, right? So it's a get element pointer and whatnot. That goes to the same backend as before, right? So the backend compiler is still the same, and in this case, the backend compiler produces very different code. Instead of dot product 4 and floating point multipliers, it generates conditional move based on which index is being used. The key bit here is we have been using the same source code, we've been using the same compiler on the same hardware, and we're getting 2 different results just because the front end in the pipeline has been different. In one case we went for FXC, in one case we went for DXC. That's why we're going to focus on the front end first, because if you make a decision in the front end phase, then this will affect the whole compilation, right? There's nothing which can undo decisions made in the front end. So front end, that's the part at the very top, right? That's where we say, if we look at the whole shader compilation pipeline, we start with this high-level language source code, it goes through the front end, some front end optimizations, produces some kind of intermediate format, which we then pass on to the driver, which is the bottom half of this picture, and the driver does a ton of optimizations on it. We're not going to go through all of them, we're just going to focus on those 3 parts here for today. So, intermediate representation, intermediate format, we've been discussing this. Why is there an intermediate representation in the first place? Well, imagine there's something like a switch statement, it has a break, well then in this case it's probably clear on the C side where this break goes to. But imagine you have a switch nested in a switch, or you have a switch nested in a 4 and you write a break. Then you probably have to look up, is this like breaking from the innermost or from the outermost scope? It's not entirely clear, but just looking at the source code. That's not good if you want to ensure that all of your source code works the same everywhere. And that's why we have intermediate representations, which are much lower level. Typically, it's very, very specific on everything. There's no ambiguity in there. And on the right-hand side, we can see the LVMIR for this case. And you can see the breaks have been converted to branches which specify the label they are branching to. So there's no ambiguity what this break is actually doing, right? It's a branch somewhere. Like it's the same as if you have written like go to and then the label itself. That makes intermediate representations very, very interesting for graphics APIs because we don't want different drivers to produce different results. And as such, all of the major graphics APIs these days mandate the use of intermediate representation. spew is the one for Vulkan, DX bytecode is the one for D3D11, and for Direct3D12 we have to use Dixel. An interesting thing to understand about intermediate representations is that the conversion from high-level language source code to intermediate representation does not have to be lossless. It has to be semantic preserving, granted, because otherwise code will then execute differently than your input. That's clearly not what you want. But it can do things like it can change the types, it can change expressions, and so on along the way. And there are actually things which have to change along the way, and those are called legalization oftentimes. Because legalization, that's the part where you make code legal in the sense you can express something in the high-level language which you may not be able to express in the intermediate representation. A very simple example for this is a division. The intermediate representations for GPUs usually don't have a division operation because GPUs don't have a division. So instead, a GPU has something called the reciprocal operation, which just returns the result of 1 over something. Now, we could force all high-level languages to do the same, right? We could just remove divisions from high-level languages. So instead of writing A divided by B, you would have to write A times reciprocal B. That's clearly not very efficient. And one day there might be hardware which has divisions, then you probably want to take advantage of them. So instead, this part is done in the front end as part of the legalization step. And in the legalization step, the front end will see a division and it will just replace it with a multiply with a reciprocal. There is, however, more stuff which is happening as part of the legalization. So legalization, for instance, can also change how the code looks like. And if we look at this very simple example here, we're calling a function and we're passing in a buffer to a function. And that's literally the only interesting bit about this code. We are passing a buffer into a function. We can compile this to spew and we will see a function call which passes on a buffer. So you would think, okay, what happened here? Everything is fine. Well, it turns out that in the Vulkan environment, this is not allowed. You are not allowed to pass buffers into functions. There is no ABI defined which supports this. And this might be actually true on the real hardware. Your GPU may not support passing it through a register because that might be implemented differently. So what the frontend has to do is the frontend has to legalize this code and make it something which is supported and validates for the target environment. And in this case, the only way to do it is to eliminate the whole buffer passing. So the way it's being done is by inlining the function call completely into the caller, and now you don't have a buffer passing around anymore. So that makes the function legal, but at the same time, it removes semantic information, right? Previously, you knew you were calling a function, right? You could look at the source code and say, okay, how often am I calling this function? Okay, 25 times. Okay, I want to put in an instrumentation into there so I can just do it and it's fairly easy. Now this information is lost, right? There is no visible function call anymore. When it comes to the backend and you want to instrument how often this function is called, you can't do it anymore, right? It's a lossy transformation due to legalization, right? It's not even because the compiler was optimizing anything. It was just trying to make things legal and it had to do an inlining, and that loses already information. There is even more going on in the front end of it, because sometimes legalization is enough to make the program run, but sometimes there are things which the API mandates which go beyond legalization. For instance, the API might say how buffers are handled. And this is a very simple example here, right? So there's a buffer with floats, and you load a float and you write a float. So you would kind of assume that what the intermediate representation will express is you're reading a float and you're writing a float. Well, turns out the API mandates a different behavior. The API mandates, in this case, behavior as if you have written buffer float 4. So that's what the intermediate representation looks like. Like in both the X bytecode and the Dixel case, you can actually see that it's producing a float 4 load and a float 4 write. And this will all work out because the descriptors will match. But what happens now is when you look at the ISA, you can see that there are 4 floats being loaded and there are 4 floats being written. And the backend compiler is bound by this decision because the backend compiler doesn't even know that you have been writing buffer float, right? For the backend compiler, it looks the same as buffer float 4. Why do APIs do this? Well, there are reasons about compatibility, ease of use, and so on, which makes it sometimes desirable to be not super strict about the types. And in this case, the way you pay for it is you pay with 3 more registers being allocated. If you bind a buffer float for buffer float 4, everything will just work, so that's nice. But yeah, in the case where you know you're binding a buffer float, then obviously you're paying those 3 extra registers you wouldn't have to pay for otherwise. And that's it for the front end. So I hope I gave you some idea about transformations which can happen in the front end, not really optimizations. And Nikolai is going to cover optimizations, intermediate representations, and static signal assignment next.
Thank you, Matthias. So let's talk about those middle-end topics, starting with static single assignment form. What is SSA form good for? To understand that, let's look at that example program on the left, which is not an SSA, because as you can see, the variable x is assigned to multiple times. This is normal and fine for programming languages, but can pose a challenge to the compiler. Imagine that it analyzes the assignment from x to z there at the bottom and wants to do constant propagation, let's say. In order to do that, it needs to know where the value of x is coming from at that point in the program. And since x was assigned to multiple times, that's not immediately obvious. Of course, you could add an analysis to the compiler to figure that out, but this kind of problem arises so often that you would have to do this analysis so often that it would eat into your compile time performance. So SSA really helps with that, because by having every variable assigned to only once, we can immediately tell where the value in each variable comes from, which means that we need to translate our programs into SSA, which involves duplicating variables, such as you can see there on the right. This duplication of variables can get tricky or seemingly even impossible in cases that involve control flow. If you look at the assignment from x to z there really isn't a single point in the program that the value of x always comes from. It depends on the control flow. SSA form solves this by introducing fee nodes. Fee nodes are virtual instructions that really don't have any corresponding instruction in hardware or in assembly language, that say at this point the value that you take should be one of those input values depending on where the program came from in control flow. Right? As you can see there on the right, that allows you to maintain the invariant that every variable is only assigned to once, even in this case. As you can imagine, that is the part where translating a program into SSA form gets difficult, especially when loops or nested if statements or other complex control flow is involved. I'm not going to go into the details, but let's look at one example here, a switch statement in which we have multiple different assignments to the result variable. And if we were to translate that program into SSA form, obviously we're going to need a fee node there at the bottom where the return statement is. Now, how many inputs is that fee node going to have? Well, the answer is 5. That's because for each of the 4 case labels in the switch statement, there is an assignment to results, and that corresponds to 1 input. But there's also the case where we take the default path through the switch statement, and in that case, the initial 0 value survives and is taken as an input for the fee node. The fee node, as shown on the screen, by the way, is what you would see in LVM intermediate representation. Okay, so now that you hopefully have a bit of an idea of how SSA form works, let's talk about some fundamental optimizations that happen in a typical compiler middle end. Those are dead code elimination. Right? It's kind of obvious that you want to do that. And if you have an instruction that doesn't contribute anything to the program, you'd rather remove it. So for example, let's say you have an arithmetic operation somewhere, and its result value is never actually used. In SSA form, it's actually pretty easy to tell that because of SSA form, the variable that the arithmetic operation's result is assigned to is only going to be assigned to by that operation, which means that the operation's result is unused if and only if there is no use of that variable. Right? That's easy to check with a simple data structure of SSA, which allows us to just remove those dead instructions. Other transforms that we're going to talk about are constant folding, common subexpression elimination, global value numbering, and strength reduction. Let's look at constant folding first. So in this example, look at that division. Divisions are expensive operations, and you want to avoid them where possible. Now, in this case, you could say, well, both sides of the division, both operands are constant. So why didn't the programmer just say, well, clearly the result of the division is 3 and write that in the program? And you could do that, but you could also argue in this case that by writing here block size divided by 2, the intent of the program at a high level is more visible. So is there a trade-off between runtime performance and having a high-level expression of the intent? Luckily, no, because the compiler, thanks to constant folding, can clean it up for you. Now, how this looks in practice is something I want to illustrate, in this case with spew intermediate representation. Now, this is spew as it comes out of the front end directly. And you can see there at the top that it defines literal constant 6, which was the block size. And in fact, even the two-component vector, both of whose elements are 6. The same with 2, and then there is an explicit division operation. Now, the compiler, during constant folding, looks at this division operation, and it looks at the operands, right? They're %9 and %11. And thanks to SSA, they are only assigned to once, and they're assigned to a constant. So the compiler can know that both operands of the division are always going to be exactly those constants. So you can just do the division immediately at compile time and replace the division by the literal constant 3. Right, so that's constant folding. Now let's look at something slightly more advanced, which is common subexpression elimination. So in this sample, you see that we load 6 times out of an input buffer. Actually, some of those loads are redundant, the same component. And even those 2 additions are redundant. And analogous to what we said before in the constant folding case, you could argue, well, maybe the programmer should extract those additions, assign it to a temporary variable, and then use the temporary variable instead. And that's a legitimate argument to make. In this particular case, it might even make the program source code more readable. But keep in mind that often you want to, for example, define helper functions to structure your program. And a situation such as the one there on the screen can easily come about after inlining those helper functions, right? And so in order not to pay a performance price for structuring your program with those helper functions, you really want the compiler to clean it up for you, and that's what common subexpression elimination does. So let's look in detail at how that works, again with spew. Now, the first thing that might be a bit surprising here that I want to highlight is the use of those image fetch operations. This is because in the original HLSL source, I used a buffer that in the Vulkan world is considered a texel buffer and thought of as an image. So in fact, for each of the loads out of the buffer, you have here an image fetch operation that loads the entire 4-component vector. Now that's a lot of redundancy there and very wasteful, but luckily we can clean it up. First of all, we see that all of those image fetch operations use exactly the same operands. And thanks to SSA, we know immediately that this means that they load from the same index of the same buffer, all 6 of them. With an additional check, which the compiler needs to do separately, SSA doesn't help there, but it's easy enough. It can tell that there is no other memory operation in between that might change the outcome of the load, right? That there's no image store there that would mess things up. So we can remove all the redundant fetches, have a single one, and extract the components from that single fetch of a 4-component vector. Of course, now we can tell that there's redundancy of those extract operations. For example, if you look at 22 and 30, those have exactly the same operands. So this means, thanks to SSA, we know immediately that they will produce the same value, and we can eliminate one of them. And this propagates through the add, can eliminate all of one of the add instructions as well, and end up with cleaned up spew. And if we compile the original shader down to ISA, we see the same thing. We end up with a single 4-component load, a single add operation, and then the 2 multiplies that were not redundant. Now, global value numbering in many ways is a common subexpression elimination that's more powerful. It can also do certain analyses across basic blocks. So in this example here, which is a bit artificial, but bear with me, we know that if we take the true case of the if statement, then did X and did Y are in fact the same thing. So we can simplify that indexing expression there. And then from there, we can even tell that the expressions are the same on both sides of the branch. So we can pull it out, lift it into the block above. And then dead code elimination can get rid of the entire branching structure, and we get much simpler code. There is one additional step that would typically be taken here, which is actually already strength reduction, which is to replace multiplications by shift operations, which are cheaper. And indeed, if we compile the original example down to ISA, then this is what we get. We get shift and shift add operations, and really quite nice and simple code. So that was global value numbering. We already saw strength reduction. More generally, strength reduction is the idea that when you have an expensive operation in your program, you replace it by a cheaper one. So in this example, divisions are pretty expensive operations, and we generally replace them by reciprocal and a multiply. And in this case, where we divide a 4-component vector by a constant scalar, in fact, we end up with a single reciprocal operation and 4 multiplies. The multiplies are full rate instructions. They're cheap. So that is a good optimization here to make. Another example, which is kind of cute, is that when you have an integer division divided by dividing by a constant, and in fact, the compiler knows some mathematical magic that allows it to turn the division into a multiply followed by a shift operation. And the multiply may not be full rate, but it's still much cheaper than doing an integer division. So this is a good optimization as well. And there is a whole host and library, of strength reductions like this that one can do, and they all help to clean up your program and allow you to express things in higher level terms. So now you've seen SSA form, you've seen constant folding, common sub-expression elimination, global value numbering, strength reduction. We've talked about dead code elimination as well. Those basic optimizations, which basically every compiler has, allow you to write your program in slightly higher level terms while not having to worry too much about runtime performance, at least at that very detailed level. There are more things one could talk about in the middle end, like loop transforms, but we're not going to go into that here. I hope you found this already interesting. And with that, let's go back to our overview map, and I'm going to hand it off back to Mateusz.
Thanks, Nikolai, and welcome back to the last part of our journey. We're going down to the dragon layer, or the backend. So the backend is the part where IR gets converted into ISA. So we have the highly optimized IR, and now we know exactly what hardware we're targeting, and we can produce ISA specifically tailored for this hardware. This means we can choose instruction based on the hardware. So if we know there is something in the hardware which is faster using a specific way, we can now pick the right instruction. But it also means we have to take the hardware into account when generating code, because the way the hardware executes code, or the way the hardware is architected, can actually impact how we have to generate ISA. I'm going to look at this in a moment. And finally, certain optimizations, which are hardware specific, can happen here in the backend and only in the backend, right? So they just pass through all of the front end stuff, and now in the backend it actually starts to matter. Let's start with the memory access. So memory access in the front end is fairly easy, right? You read from a location, you write to a location, you read again, you get the new value. So some things like the Vulkan memory model might tell you, okay, I need to issue a kind of barrier in there. But generally speaking, this is how things work, like especially in D311, for instance, or where there's no special barrier defined for all of this kind of stuff. The hardware doesn't look like this, right? So the hardware actually has separate caches. So if we look at RDNA, there is a K cache and there's an L0 cache, and they are not coherent with each other. The K cache is read-only on top of this. So this means if you read a value, you could read it from the K cache. Then if you write to this value, you write into the L0 cache. If you read again and you issue another K cache load, you will read from the K cache, and that will read the old value, because there has been nothing which said, okay, the K cache needs to be flushed in the meantime. And probably you don't want even to flush it, right? So if we look at this very simple code snippet here, so we have a read-write buffer, which is only read from. We have another read-write buffer, which is only written to, and we have a constant buffer. The rules say read-write buffers can always alias. So that means the backend needs to ensure that this code works in all circumstances. What does the backend do? Well, it knows about how the hardware looks like. It knows about the rules of the API, and now it generates the optimal code. So it says for the constant buffer load, I can issue a scalar load because that's read-only. It goes from the K cache. None of the writes I'm executing here can actually alias the data. So that's fine. For the read-write structured buffer, even if I'm only reading from it, I cannot issue a scalar load, because if a scalar load gets issued, then this might read stale data. So the shader compiler will issue instead a buffer load, which goes from the L0 cache. And everything works fine, but you have to be aware of this, right? Because this is now the backend compiler making decision based on the hardware. Like imagine if the hardware had no K cache, it wouldn't matter, right? If you have a constant buffer or read-write structured buffer load, they would all go for the same cache. But because they're different caches and the hardware looks like the way it is, you have to be aware of this when writing your code, because if you make a constant buffer load and it goes through the scalar cache, that's obviously beneficial because you use an additional cache and additional hardware resources. Another thing where the backend has been, or the hardware has been influencing the whole compilation pipeline is, we saw those texture addressing and texture filtering instructions today already in the front end. Because in the front end, what we saw is if you have a buffer load, it actually turns into a buffer 4 float load, right? So why does this happen? Well, because buffer loads go through the texture unit, and the texture unit always loads 4 values anyways, so it's kind of free to just load 4 values. And that's how the whole API was designed, right? For convenience, and because the unit already returns floats anyways, you just always bump it up to 4 basically. But that's not the case for all the loads, right? Some loads can go through a more specialized hardware unit, and then the backend decides how to do this, right? So the backend could always say, I'm always go make float 4 loads, right? But for the buffer load, the frontend made the decision, but for a structured buffer, for instance, the backend could still decide to generate the same code. But because the hardware actually supports something else, the hardware does support single float loads, then the backend picks the right instruction. In this case, it will issue a buffer load, right? So that's important to understand, right? So the specifics of the hardware can influence the right instruction selection, right? You could imagine hardware which doesn't look like this, and then you could generate the same code for both cases. But because the hardware does actually support this, it's important for you to understand what is the ISA being generated for this particular type and so on, who along the shader pipeline changes this, and how it impacts code generation. And in this case, using the structured buffer load will save you 3 registers. So that's good. The next thing we have to look at is how stuff executes on the GPU, right? Because a program, when it executes on the GPU, it executes very differently from a CPU. Because the GPU is split into 2 parts, right? There's a thing called the scalar unit, and there's the SIMD, which is the vector ALU. If we zoom in for a moment, then we can see the scalar ALU. It's one unit shared across all 32 vector ALUs. The scalar ALU has its own register file, and the vector ALU has another register file. The vector ALU stores 1 value per vector ALU unit lane. The scalar unit also stores 1 value, right? The vector register is obviously 32 times bigger. And you can turn on and off individual vector lanes using an execution mask. All of this matters now for even very simple code, right? So if I write code like this, so I just write a branch, you would assume from the front-end side, well, there's nothing to worry about, right? Okay, this is like super simple. But the backend needs to understand if this is a scalar branch or if this is a vector branch. Why? Well, if it's a scalar branch, it's very simple. It will execute a scalar comparison, it will execute a scalar branch, and it will jump across code. So it will not fiddle around with this execution mask, it will just jump across code because that's all that's needed, right? All of the lanes are active, we execute a jump, we jump to the new location based on the branch decision. Problem solved. If the input is varying, however, which means there's a different value per vector ALU, then suddenly this doesn't work at all anymore, right? Because if we can't do a scalar branch across a vector value, which one would you branch around? Like imagine lane 0 says yes and this lane 1 says no. So what the compiler has to do instead is it says, okay, we have to do a vector comparison, that's the first thing, so we have to use a VGPR instead of a scalar register. And then we have to fiddle around with the execution mask, because we have to execute the true branch, then we have to flip it around and execute the false branch. And one thing to notice here is that the compiler is issuing additional scalar branches in here. And you might be wondering, how can a compiler issue a scalar branch if this is a vector varying instruction? And the reason is very simple. Even for its varying instruction, it might happen at runtime that all of the values are the same, which is called it's dynamically uniform, in which case the result of the comparison will be all zeros or all ones, and then things can go faster. Generally speaking, this won't be the case, so you will get behavior like this. So you have some lanes being turned on and off, then you switch it around and then the other lanes are being handled. But it could happen, and the compiler assumes this is likely enough to happen, and it will issue a scalar branch on top of it. This is an alternative compilation of the same code, right? So if the compiler would assume that this is never going to be dynamically uniform, then it will probably produce code like this, where it doesn't introduce scalar branches at all. They are rather cheap, but still, if you know, like, it's always 50% of the lanes are going down one path or the other, this would be better code. And this is something you have to be aware of, right? If the backend can make decisions about how your code looks like, and you can infer, okay, this is super varying or this is not super varying, then the backend can make different decisions occasionally. This is very hard to control. That's important to understand here, that this is not something you would typically target for, but this is something where the backend has freedom to choose. And we've been talking about varying and uniform so far now, and one important thing to understand here is like, uniform is the difficult case, right? So uniforms are scalars, and only combining scalars with scalars will yield scalars. In all other cases, the compiler has to go to varying or vector registers again. And this is the whole reason for all the research about scalarization, which is about how to go back from this. We'll get to this in a moment. First, we will look at how this vector varying property and the uniformity property impacts code generation. If you remember the example I just gave you about loading from a constant buffer, a load from a constant buffer with a uniform index will lead a scalar load. Clearly, because it's all scalar, but it's uniform, you can use a scalar load because we're only loading one value. Everything is fine. Loading, so we can see it here, right? It's an S buffer load. Loading a constant using a varying index, however, even if it's a constant, we cannot load the same value anymore, right? So we need to issue a varying load, which means we have to go through the vector unit, and bam, we're getting a T buffer load in this case, which loads a different value per lane. And that's very important to understand, right? Because if you remember what I said in the front-end discussion, is this like if we know it's a buffer which can alias another buffer and so on, then it can pick a scalar load and so on. But if you issue a varying load, then even though technically you expressed everything right, the fact that the hardware executes in this way will trigger the different kind of load. And knowing when something is uniform or varying is not very simple for the compiler, right? You would assume that, okay, all the inputs are varying or uniform, then the compiler can just infer the sum for the whole code. But the problem is control flow can turn uniform variables into varying variables. And that's very difficult for the compiler to understand and optimize around, right? So the compiler knows what's happening here. It will always err on the side of safety. And in this case, for instance, it has to go varying from uniform. So if we look at it, it starts with uniform, it's on a scalar register, and then when things happen, like this branch, which is based on a varying and a uniform component, it will turn the uniform scalar register into a vector register, and then afterwards it's a vector register from this point on. And that's important to understand, because this is the one direction, right? Uniform to varying, and we will learn later how we can undo this transformation if we know that this value is uniform again. So as just mentioned, going from scalar to uniform is very simple. The compiler will do it all the time because it wants to be conservative, doesn't want to break your code. The other direction is what is called scalarization. So that's when you have seen a GDC presentation about read first lane or read lane, that's going from varying to scalar. And I hope you understand at this point that why this is not a trivial thing to do, right? Because it means you understand how the control flow looks like, you understand how the data flow looks like, and now you can make this jump. Sometimes, however, the compiler can do it actually for you for free. So here you have an atomic instruction on a buffer, and the compiler will scalarize this automatically because it's now exactly what's happening. So what's happening here is like every vector lane wants to add a value to it. But what we can do instead is we can reduce across all vector lanes using subgroup operations, and then we can issue a single atomic on one lane, which happens to be active, one of the lanes, which one doesn't matter, and we have scalarized the code completely automatically. So for instance, for this kind of code, there is no point in scalarizing yourself because the compiler can do it safely. And this is one of the very few cases where the compiler can actually do it very safely itself. Another part where the compiler does not do it by default because it's expensive, but where scalarization is important, are waterfall loops. So I have a texture array like this, and I'm accessing with a non-uniform value. So it's a varying value, it can vary per lane, and I want to load a different descriptor, then there's a problem. Because on the underlying RDNA hardware, descriptors are scalar registers. So they are uniform across the wave. But in this case, what you would like to have is a register per lane storing the descriptor, and that doesn't work. So in the very front end, you tell the compiler this is a non-uniform load. What the compiler will do for you is it will generate a loop which loops around this load instruction and will execute as often as there are different values in those vector lanes. So if your vector ALUs have, for instance, two distinct values across all of them, so like every second one is using another texture, and the compiler, then this loop will only execute twice. And the compiler can combine those loops and split those loops as it sees fit, but it's important that you convey the information to the compiler so it can do the right decision. Because if you scalarize yourself, the compiler is unable to optimize anymore, right? So if you leave the freedom to the compiler, we can do things like, if we do this for two instructions consecutively, we can merge both of those loops together and execute them more more efficiently. Or we can split them up, and so on. You can also scalarize manually, and that's when you know something is dynamically uniform, right? So you know you're reading something which will be true and the same for all of the values in your vector, even for you loading with a vector index, for instance, and for some reason this happens. So in this case, you can manually scalarize, and then things like wave read lane first happen, right? This is where you just write it in and you say, tell the compiler, okay, the first value in the wave, so the first vector register which is active, that's a uniform value, and you can just promote this. And you can see this. The value gets promoted to a scalar register, and the compiler issues a scalar branch, doesn't do all of the vector magic anymore, and you get the behavior you want. And that's it for the backend. So I hope I got the idea across is that the way from the front end to the back end, it's a very, very long journey. And along the way, we lose a lot of information, we lose types, we lose instructions, we lose expressions and whatnot. We have learned about the static single assignment form, which is underpinning modern compilers, and it's critical to understand because that's where all the constant folding, that code elimination and so on happens. And it allows for many, many optimizations to be done in the backend and in the middle end automatically, so you don't have to do them yourself. And in the backend, we have hopefully conveyed to you that the underlying hardware does matter, right? What kind of load gets issued is important. How the hardware executes is important because scalarization can or cannot be a thing. Sometimes the compiler can scalarize, sometimes it can't, and sometimes you can help it. And it's important to understand why this is happening in the first place and what are the places and the methods to actually support it, right? So I showed you how wave read lane add or read first lane can help you to scalarize code again and why you would want to do this. And with that, thanks for your attention and see you again sometime in the future.